Hey everyone, this is your video for your Unit 5 study guide. So question number 1, does the number of electrons in an orbital depend on its shape? No, it does not. The key word here is orbital, and that's the sort of thing you want to look for. And we know that orbitals can only contain 2 electrons. It doesn't matter if they're in an S sublevel, a D sublevel, all orbitals can only hold 2 electrons. Question 2, defining an orbital. Put a couple of things down here. A three-dimensional space surrounding the atom where electrons are most likely to be found is an official definition. You can also think of it as a space within a sublevel where only 2 electrons may be maximum. Number 3, what does the Heisenberg uncertainty principle state? That is the one where it says that you can't know both the position and velocity of an electron at the same time. If you try to measure one, you disturb the other, and vice versa. Number 4, what are valence electrons, and how do you know how many valence electrons an atom has based on its electron configuration? Well, valence electrons are those in the outermost energy level of an atom. And you can determine how many valence electrons an atom has based on its electron configuration by determining the highest occupied orbital. Occupied orbital means the one in the principal energy level that actually has electrons. And then you total up all the electrons in all the sublevels of that energy level. So off to the side here, I've put an example electron configuration. So it says step 1, determine the highest occupied orbital. So we're going to determine the highest. So we have principal energy level 1, 2, or 3. So that means energy level 3 is the highest energy level that is occupied. Then you total the electrons in all sublevels. So you're going to take the 3 electrons in the P sublevel and the 2 electrons in the S, add them together, and this atom has 5 valence electrons. Number 5, how can atoms be identified from their atomic emission spectrum? You guys did this in your flame test lab. You looked to see the actual colors so you could match them up with the names, and then when I gave you unknowns, a lot of you were able to correctly identify them because each color is unique to the specific atom. So now bringing back a little bit of review, what quantity identifies the atoms of a particular element? And you've got a little hint there. If this number differs between atoms, they're not the same. The only thing that changes an atom is atomic number. Number 7. Back when scientists first observed these atomic emission spectrums, the lights, what were they seeing? Explain what was going on with the electrons. So I've drawn a little picture here. We have an atom in its ground state, which means the electrons are on their lowest energy level. So I've drawn an electron on this inner energy level. And if you add energy, then the electron ends up on its outer energy level, which is the excited state of the atom. It's gained energy and it's able to jump to the outside. But it can't stay out there. When that energy is released, so we're headed back this way, that release of energy is shown in the form of light, and the atom returns to its ground state. So that's what's going on with the electrons. They make a quantum jump to the outside, so jumping from here to the second ring to here, and then when that energy is released back to the ground state, you see the light. So your next question says draw an example of an atom in its ground state and an example of an atom in its excited state. Guess what? You just did. There they are. And number 9 says explain what Niels Bohr got correct in his model and what he got incorrect. Well, we talked about him quite a bit, and we said he was correct about this whole ground state, excited state thing, about adding energy, and when the release of energy happens, you see energy in the form of light because the electron releases photons. And we talked at length about how he was incorrect. He thought that electrons travel in circular orbits, and we know that they do not do that. For number 10, how did Schrodinger's model differ from Bohr's? Schrodinger's is the later model, after Bohr's, and so Bohr believed they traveled in circular orbits, but Schrodinger believed that they traveled as waves, and he was right. His model matched up all atoms, not just hydrogen. Okay, moving right along. Number 12, what are the 3 rules we use when filling orbital diagrams and how do we show them? Rule number 1 is the Aufbau principle, and we talked about the Aufbau order. He's the one that says electrons fill from lowest energy level to the highest, so they go in this order. Number 2 is the Pauli exclusion principle, which says if electrons are in the same orbital, such as this, both of these electrons are in the 1s, then they have to have opposite spins. We show that with the different directions on our little arrows. The third rule is Hund's rule, and that's the one that says that you fill each equal energy orbital, so such as the 2p, like I've written here. These are equal energy orbitals because they're all within the 2p sublevel. And so we fill them up one at a time first, and then start doubling them up. So, writing electron configurations for each of these atoms, the way that I would go about this, if I were you guys, now that you have some experience, is I'd first take a look at your periodic table. Sodium is the one that you're looking for, so locate it on your periodic table. And what I like to do is determine what I need to end with. So I know that this sodium atom is going to end its electron configuration in the 1, 2, 3 S, because it's in the S block, 1. Okay, so my electron configuration is going to end in energy level 3 because I count down 1, 2, 3. Sodium is in the S block and it's the first one, so 3s1. So now that I know that, I just kind of write that off to the side here. And you kind of get the rhythm in your head. And so you kind of get this rhythm in your head from the periodic table. And so if you like doing it this way, this is a really good way to do it. So remember your 1s2 across the top, 2s2, 2p6, 3s1. And you also got your order up here, very handy. So all you have to do is follow your order. Count your periodic table squares. 1s2, 2s2, 2p6, and we said we end on 3s1. 3s comes next, so 3s1. Just like that. So that's the method that I use to do all of these. Then next question, drawing the orbital diagram. So orbital diagrams for oxygen, again, refer back to your periodic table. And if you look at oxygen on the periodic table, it's in the P block, and it's in the second row down. So I'm going to end in 2p. So that tells me how many orbitals I need to draw. So I go clear through my order, 1s, 2s, till I get to 2p, and I can stop. I look at oxygen on the periodic table, it's number 8, so then I just count up my electrons. 1, 2, 3, 4, 5, 6, 7, 8. Remembering those rules that we talked about on number 12. So that's the method that I use to do all of these. So now we can go on to number 15. What element does each of the following represent? And so I'm going to use number 1 as my example. So what you want to do for this is go all the way to the end and look at the last energy level and sublevel. So it says to go to 4p4. So on your periodic table, this is the P block. So we know that our element is going to be in there somewhere. And earlier we said that the energy level is by row. So 1, 2, 3, 4. So this is the 4p row. So that's also where our element is going to be. We just narrow it down. And then it said 4p4. So that's where 4p1 is. So then 2, 3, 4. So that narrows it all the way down. It's in the 4th row, P block, 4th one over. So this one is selenium. And I did all of these that same way. Okay, determining the valence electrons and draw the electron dot structures of each of the following. Using boron as my example, the first thing that I would do in trying to determine valence electrons is write your electron configuration. For boron, this is it. So for valence electrons, I'm going to go to the highest energy level, which is 2. And I'm going to total up those electrons. So boron has 3 valence electrons, 1, 2, 3. And so to write the electron dot structure, there you go. Remember that those dots could be on any side, just remember you go one side at a time before you double them up. And that's how all of these were done. Number 17, the orbital diagram has arrows pointing in opposite directions when 2 electrons occupy the same orbital. What do these arrows indicate? Well, we talked about these rules on number 12, and so when 2 electrons are in the same orbital, according to the Pauli exclusion principle, they have to have opposite spins. So the arrows pointing in opposite directions show those opposite spins. Okay, element X. Okay, a couple of students made me aware of what happened here. They saw these dots and they realized that they should have gone into these places, so I just drew arrows where they're supposed to be. So that means that this electron dot diagram has 5 valence electrons in it. So you have to try to pick out 2 different atoms that could have 5 valence electrons. The 2 that I chose were nitrogen and phosphorus. If you understand the pattern, you'll be able to tell there are several more that could have been possibilities. Identifying the element that has the following orbital filling diagram. So it's just kind of skipped the earlier ones and they're on the end here. So 5p4 is where you want to end up. So if you look at your periodic table, in the 5th row down, in the P block, 4th one over, it's tellurium. Okay, correctly drawing each atom as if you had taken a picture of the model. The way that I would go about this is, again, first doing your electron configuration. It's basically a roadmap of everything. So for nitrogen, this is the electron configuration. And I can use this as a roadmap to draw my atom. So I draw my nucleus in the middle, and then my first energy level. Well, here is energy level 1 in my map, and it says that there's 2 electrons in it. So I go ahead and draw them. And then I go up to energy level 2, which is all I need to go to for nitrogen, because it doesn't go to energy level 3. And I see that there are 1, 2, 3, 4, 5 electrons in level 2. So I go ahead and go 1, 2, 3, 4, 5. And so nitrogen has an atomic number of 7, which means it should have 7 electrons. And that's what your drawing should show. 1, 2, 3, 4, 5, 6, 7. I don't need a 3rd ring because nitrogen's electrons don't go into the 3rd energy level. So use your electron configurations to make this easy for you. That's how I've done all of these. So here's your final page. I hope this was helpful for you, and I hope that you will please come to me if you still have any lingering questions. I'm here before and after school every day, so if you're having trouble, please don't hesitate to ask. It's better to ask than to have trouble on the test. I'm happy to help you guys, and good luck studying.